Hi friends, welcome to my channel in Advanced RTL Coding. So without wasting much time, let's start understanding the RTL design problem 2. So this problem is the extended version of the problem 1. We are making this design more parameterized and generic. Instead of converting the hard-coded 8-bit into 2-bit or 16-bit into 4-bit or 16-bit into 2-bit, we are just giving the parameter value, and based on that the whole design will work automatically. Like if you give the input bit 16 and output bit 4 or 8 or 2, so accordingly the design will work accordingly. You don't need to change the other variable value or other um, state values. So other things are conditions are same, and the FSM will also be the same as what we used in the problem one. So if you have not watched the problem one design or video one where I have uh, explained that how to convert 8-bit data into 2-bit. So there I have explained this FSM in detail. So you can just watch that video and then you can continue on this video as well. So let's move to RTL design. So this is the module name Citrage 8-bit. This is the input data width, output data width. These are two parameters I have declared. So based on that, the input data width di and the output data width data out. So these data width will be declared automatically. Only you have to change the parameter value. These are the port list of the module, and the clock count, like to convert in input data width into output data width, how many number of clock cycle will be required. Suppose 16 data width you are want to convert into 4, so that should be 16 divided by 4. So you need 4 counts, 0 to 3. So count bit should be 2 bit. So you have to take the logarithm of the clock count. So suppose 16 divided by 4 is 4. So of log 2 of 4 will be 2. 2 minus 1, 1 down to 0, that is 2 bit. 2 bit will count 0 to 3. These are the FSM states, and the data out. You can see in the problem 1 I was hard coding the multiplier value 2. Here you can directly multiply it with the output bit and whatever the data bit is required. So, so the bit slicing works like this is 4. So the width of this signal will be 4. It will slice 4 worth of the data from starting index. Whatever the starting index will be calculated here. So for count equal to 0, the starting index will be 0. So width is 4, so it will count 0 to 3. For count equal to 1, the starting index will be 4. So it will start from 4 and it will count next 4 values. So 4, 5, 6, 7, and 4 to and count for count equal to 2. It will start from 8 and it will go till next 4 value 8, 9, 10, 11. And for count equal to 3, it will be 4 into 3 or 12. It will start from 12 and will go to its 4 value, that is 4, 12, 13, 14, 15. So that is how the bit slicing will work. The valid out will be assigned when we are into the correct state, and there is no valid error and there is no input validation. And reset count, instead of writing the hard coding the value, we can directly put the clock count. So you can see only we need to change this value. After that, everything will be taken care of the design. So where we have to change, wherever we are instantiating this module, we need to update the parameter values. Okay, and this is the state transition, according to the whatever FSM we have designed. And this is the next procedural block where in every state what should be the count value. So in the idle state the count should be 0. In the data state, if there is no reset count asserted, then it will keep incrementing based on whatever value was there in the clock count. So if it will be reaching the value clock count equal to clock count minus 1, it will move to idle state again. So the count will become 0 again. So that is how it is implemented. Now let's move to the test bench. So in the test bench, you can uh, pass the input data bit and output data bit. Accordingly, the design will convert and what input bit to output bit, whatever value. So here I'm passing 16 and 4, and clock delay is 16 divided by 4. So accordingly, it will generate the test bench. Okay, and this is the waveform. You can see here at this valid if you want to check. So initially valid is for more than 2-3 clock cycles. So there will be valid error at every alternate clock cycle, and there will not be any valid output generated. So once the valid is high, there should not be the next valid till the count maximum count value. So here we are converting 16 bit to 4 bit. So count will be increment from 0 to 3. So next valid is coming after the count reset to 0 again, 3 to 0. Then there will be no valid error. And you can see this is the data in. So here you can see 3 down to 0 is your first data, that is 0 0 1 1, that is 3. So 3 will be your first valid data, and then 7 to 4 is 0 1 1 0, that is 6. 6 will be your next data, and then 11 to 8, that is again 0 1 1 0. So you can see 6 is last for next clock cycle as well, and then 15 to 12. 15 to 12 is 0 1 0 1, that is 5. You can see it is 5 at the output. This is the 5. You can see 5. After that, output is changing, but there is no output valid, so it doesn't matter. You can see valid out is reasserted after the 5. So 5 will be the last valid value at the output bus. So first will be 3, and then 6, and then again 6 and 5. That's how it works. So to understand more challenging problem like this, please like and subscribe my channel. Thanks for watching.